an invitation. So throughout the talk, most of the talk will be over complex numbers. So I'd like to start with a very simple example. So here we have a 6x6 skew symmetric matrix. And you compute its determinant. It's going to be given by the square of the Pfaffian, which is a cubic form. And now let Y be the vanishing of this cubic form as a cubic hypersurface in P4. And this is the classical Klein cubic threefold, which is the unique smooth cubic threefold with automorphism group PSL to 11. It has order 660. It's a simple group. And in general, a degree D hypersurface in Pn is called Pfaffian if it is given by the vanishing of a Pfaffian of some 2D by 2D skew symmetric matrix in linear forms. Pfaffian is just the square root of the determinant in this case. The reason why these Pfaffian hypersurfaces are of interest is that it puts extra structure on this hypersurface. So each of the skew symmetric forms, the skew symmetric matrix correspond to skew symmetric bilinear forms, and that corresponds to certain rank 2 vector bundles on Y, as we'll explain soon. But for this talk, we will focus on the case n equals to 4, d is 3, and Y is smooth. That is a smooth cubic 3. So that means we need a 6x6 matrix, and so we need some vector space of dimension 6. Now we also need the space of skew symmetric bilinear forms on V, which is denoted as wedge 2V dual. This is a 15-dimensional vector space, and let's give it coordinates Pij with I and j runs through 1 to 6. So now each of the point on the vector space corresponds to a skew symmetric form. Well, corresponds to a skew symmetric matrix by n. And each of them will corresponds to a skew symmetric bilinear forms on V. And we define the universal Pfaffian as the cubic hypersurface given by the vanishing of Pfaffian of this matrix N in the projectivization of wedge 2V dual, which is P14. So this is a 13-dimensional cubic hypersurface. So since it's given by the vanishing of determinant, each of the skew symmetric forms corresponding to a point on the Pfaffian will be degenerate, meaning it has rank smaller or equal than 4. And it turns out that the singular locus of this hypersurface parametrized the skew symmetric bilinear forms of exactly rank smaller or equal than 2. So now we want to study cubic threefold. Let's given a Pfaffian cubic threefold Y. So this gives a 5-dimensional subspace in the wedge 2V dual. So namely, you can just realize Y as the linear section of the universal Pfaffian with some P4. And since Y is smooth, each of the point will correspond to a skew symmetric forms of rank exactly 4, because if it's smaller, it will be singular. So, and this also gives rise to an embedding from Y to the Grossmanian 2V, namely you put any points in Y corresponds to a rank 4 form, and therefore the kernel has dimension 2. So now we can look at the rank 2 vector bundle over Y, given as a subbundle of the trivial 6-dimension bundle Y times V, and consisting of points Y and V, such that Y is a point on the cubic and V is in the kernel of the symmetric form it corresponds to. So we also have a canonical projection to V. And recall that Y is given by the intersection of universal Pfaffian and some linear section, P of A. Now we can also look at the dual picture. Let's put X as the intersection of Grossmanian 2V with the projectivization of A perp, where A perp is the annihilator of A. So each point on A is some bilinear form. So we can consider this annihilator. So A perp has 10-dimensional, so P A perp is P9. And after the Plucker embedding, you can embed Grossmanian 2V into P of wedge 2V, which is also P14. So both of X and Y lives in P14. So, and if it's very classical that if Y is general, X is a smooth Fano threefold of degree 14, index 1, and Picard number 1. Now, on the Grossmanian 2V, we have the rank 2 tautological bundle. Let U be the restriction of the tautological bundle to X. So on the right side, we have a similar picture. We have a rank 2 bundle over X, and we also have canonical projection to B. And so here's a few results. The proof of these theorems are more or less through linear algebra or multilinear algebra. So first is the image of psi and phi of the canonical projection actually coincides, which is a quartic hypersurface in V. Here, equality is physical equality. They are actually the same thing in V, not only isomorphism. And then it turns out phi and psi are both isomorphism in the complement of the singularity of Q. And therefore, these two maps are birational onto their image. And for that, we know the vector bundle E and U over X and Y are actually birational to each other. And it's also a classical result that the base y and the cubic and the degree 14 funnel is also birational. So one way to see it is you can pick up a hyperplane section in V. Then there's a very natural map from Y to V intersect H. So remember, each point on Y is a skew symmetric bilinear forms of rank 4. So the kernel has dimension 2. You take the kernel, you intersect with H, it becomes a dimension 1 subspace. After projectivization, it's a point. Similarly, on the right side from X, well, at each point on X is a two-dimensional subspace in V because it's inside of Grassmannian 2B. So you have a similar map. And rho and theta will be birational map, but the indeterminate locus is when your two-dimensional subspace unfortunately lies completely into H, so you don't cut off any dimension. So this means the indeterminate locus is given by the intersection of Grassmannian 2H and P4. And these will be quintic genus 1 curves generically. So this also gives a more geometric interpretation of these birational maps. This is due to Fano-Iskowski. So for any smooth cubic threefold, and so first they show for any smooth cubic threefold, Y contains a normal quintic genus 1 curve. And then the linear system of 7 minus 4c on Y defines a birational map from Y to X. X is the smooth funnel of degree 14. And the inverse is given similarly by some linear system on another genus one, quintic genus 1 curve on B, on X. Okay, so these are all very classical constructions. So now the question we're interested in is which automorphism groups of smooth cubic threefold actually fits into this construction. So I'll explain what do I mean by that. But first, I'd like to recall you that there's a classification of automorphism group of the smooth cubic threefold. So it's a result by Wei and Xu, very recent. So they show that the groups which can act on the smooth cubic threefolds are subgroups of these following groups. We have 1, 2, 3, 4, 5, 6 of them. So for PSL 211, you're already seen it acts on the Klein cubic threefold. For example, the first one, C3 to the 4th power semi-direct S5, acts on the Fermat's cubic threefold, which is the diagonal cubic. So what do we mean by when the action arises from the Pfaffian? So here we consider a finite group acting on P5, or it's just some 6-dimensional projective representation. So this gives an embedding of a group G into PGL6. We can find its preimage in GL6. So then V and wedge 2V dual will naturally be G-tilde representations. Now we want to find some 5-dimensional subrepresentation, which is G-tilde invariant subspace. And then we take the intersection with the universal Pfaffian. This will carry us a G action naturally. So ideally, we start with some G action on P5. We want to end up with some action on smooth cubic threefold. But there are a few places which could go wrong during this construction. So we need to check first. We need to check if B and A actually exist. So if your group actually acts on P5, and if there is a 5-dimensional subrepresentation for wedge 2V dual. So these are not guaranteed. And then we also need to check if Y is a smooth cubic threefold because the 5-dimensional subspace is fairly special. It's a subrepresentation. The intersection might have the wrong dimension or the wrong singularities. And lastly, we also need to check if the G action on Y is generically free. So, but these are not hard tasks. This can be basically done using a computer. So we implement a little algorithm. So we start with a group which occurs in one of the lists in the list by Wei and Xu. So first we need to find all the 6-dimensional projectively linear representations of G. That is an embedding of G into PGL6, but there are only finitely many of them up to conjugation. So this is a finite task. So for each of them, we need to find the left G tilde in GL6 and compute the representation wedge 2V dual, but that's also easy. So now for we need to find 5-dimensional G tilde subrepresentation. There are only finitely many of them up to isomorphism, and in each of the isomorphism class, it's gonna we only need to take a general one because we want to check smoothness. So we run through all the 5-dimensional subspace, a subrepresentation. We check if the intersection with universal Pfaffian a smooth cubic threefold as we desire. We also want to check if the G action on Y is generically free. It means any elements in G does not act trivially on Y. So if we get some output for some V and A, all these answers are yes. It means we start with some action of G action on P5, and we end up with an action on a smooth cubic threefold. And in this case, we say the group G admits an equivariantly Pfaffian action on a smooth cubic threefold. So we implement this process and check for all the groups. Here's what we found. We show that a group G admits an equivariant Pfaffian action on a smooth cubic threefold if and only if it's one of the subgroup of the following 4 groups: PSL211, C3 semi-direct D4, F5, which is the Frobenius group of order 20, and C5, the cyclic, C8, the cyclic group. And you can compare with the automorphism group of smooth cubic threefolds. Not many of them are realized, and these are very small groups, maybe except PSL211. So the reason we care about equivariant Pfaffian actions is once we have such an action, once it arises from a Pfaffian construction, all the action naturally lifts to the vector bundles as well. And for vector bundles with G actions, we have a nice result, which is no-name lemma, which was mentioned in Tim's talk yesterday briefly. So here, there are many versions. I stated the one we needed. So let G be a linear algebraic group and E be a G linearized vector bundle of rank R over X with X projective. And G linearized means we have a group action generically free regular on both the base and vector bundle, and the induced action on the fibers are all linear. So if that happens, we have a birationality in G equivariantly from the vector bundle and X times AR. It means we can split off the fibers with a trivial action, G equivariantly. So yeah, this means there exists a G equivariant birational map between E and X times AR with trivial action on AR. So the idea is we want to apply this lemma to the vector bundle U and E. But let's look at this diagram and the actions on them. So we start with the G tilde action on V. They naturally lifts to the action on the vector bundle E and U. And therefore the diagram is a G equivariant, G tilde equivariant. And the birationality, as I explained before, holds equivariantly with no problems. This means the vector bundle E and U are G tilde birational, which means there are G tilde equivalent birational map between them. Or we can take the projectivization, they will be G birational. But the little problem is on the base, we have projective variety. So the group G tilde will not act. What will be acting is G, because we just mod out by the scalars. And therefore, this vector bundle is not equivariant because the action on the base and on the vector bundle are different. The group which is acting is different. So we do not have no-name lemma here, and also the birationality of Y and X equivariantly will not hold in general. I will explain that more detail later. So, but one way to remedy this is we can take the we can multiply our vector bundle by V, which is a G tilde representation. And in that way, we have a G tilde action on both of the vector bundle and on the base. Now no-name lemma is applicable. We can apply it. We know E times V is G tilde birational to V times Y times A2, where the action on A2 is trivial. And then we take projectivization, PE times PV will be G equivariant birational to Y times PV times P1. And the same thing works on the right side for the vector bundle U. We also have this birationality. But recall that PE and PU are G birational. We therefore obtain the birationality between Y times PV times P1 and X times PV times P1, G equivalently. So to summarize, what we did is consider an equivariant Pfaffian G action on a smooth cubic threefold. Let PV be the corresponding the corresponding G action on P5, which arises from the Pfaffian construction, and X be the dual smooth Farman threefold degree 14. We have this G birationality between Y times PV times P1 and X times PV times P1, with trivial action on P1. So one of the motivation we want to study, so we call this twisted stable birationality, but one of the motivation is without these factors of projective spaces, the G birationality will not hold in general. And I will show you the example where when it fails. But also one might ask another question is, does the stable birationality hold in the usual sense? That means does Y times PM G equivalent to X times PM for some integer M and trivial action on P. So this differs from our results because we need an extra copies with a non-trivial action projective spaces. And this is still open.
Can I ask a question? Do you know if you need the P1?
Yes, P1. So our result we need the P1 because that comes from the no-name lemma. But without P1, not sure if that holds. But we can have Y times PM. So we can have this holds, but with non-trivial action on PM. It's basically the same construction, but we don't know about stable birationality. Okay. Now let's look at the four groups, which we know acts equivariantly, which arises from equivariant Pfaffian construction. Recall the rationality construction between X and Y. It depends on a choice of hyperplane V. This means if we can choose the hyperplane H to be G tilde invariant, so the induced map rho and theta will be also G equivariant. And this means if the representation V has a one-dimensional subrepresentation and therefore also a five-dimensional subrepresentation, we will have actually the equivariant birationality, G equivariant one from between Y and X. And this actually happens for the group F5 and C8. So now let's look at the remaining two groups. So first of all, the PSL211. So to recover the Pfaffian construction, we actually need to start with a larger group. Let V be an irreducible six-dimensional representation of SL211. So this induces action of the PSL211 on P5 because the center C2 will act as a scalar on V. So after projectivization, it becomes trivial. So now we compute the wedge to V dual. It splits into a sum of a five-dimensional and a 10-dimensional subrepresentation. So we want to choose a five-dimensional subrepresentation, but there's only one choice, which is V5. We put A to be V5 intersecting with universal Pfaffian. We get a cubic threefold with the PSL211 action. Since such cubic threefold, smooth one, are unique, we know this is the Klein cubic threefold. So this is how we can recover the Klein cubic threefold equivariantly from the Pfaffian construction. Here's a theorem by Blanc, Chaltsov, Duncan, and Prokhorov. They show that Y and X are not, so X is the dual degree 14 Farnow. For the group PSL211, they are not G equivalent birational to each other. What they show is much stronger. They show the G action on both Y and X are super rigid, but what we need is non-birationality here. So let's look at the other group as well, C3 semi-direct D4. So we can consider V as a six-dimensional representation. But here it turns out we need also to start with the larger group, C, which is C3 times, or C3 semi-direct D8. Again, it's a double cover of the original group because there will be a C2 which acts as a scalar. We chose a two-dimensional irreducible two-dimensional and irreducible four-dimensional representation of the group G tilde. This is the character of the corresponding representation. Then we can compute the wedge 2V dual. And we compute them, it splits off into a sum of many one-dimensional and two-dimensional ones. So here UIs are one-dimensional subrepresentation and WI are two-dimensional representations, irreducible ones. So now here there are infinitely many five-dimensional subrepresentation, and even and there are many but there are only finitely many of them up to isomorphism, but there's still many of them, and then every choice of a five-dimensional representation will work here. So we need to choose a very specific one, which is okay. I didn't specify the character of these the choice here, but it's a specific choice. We did it. We take the sum of U1, W1, and W2, and then intersect it with the universal Pfaffian. We find it's also a smooth cubic threefold with a G action, where G is C3 semi-direct D4. Then we also show that for the group G, the Y and X are not G equivariant birational to each other. The proof uses Burnside obstructions. I will not explain in detail. We will see it in Yuri's talk a little bit more. But the idea is there are certain divisors on Y with non-trivial stabilizer, which will be a cubic surface, which does not appear in X, and that will be an obstruction of a G birationality between X and Y. And another thing is our theorem actually works for a much smaller group. So the group C, there's a subgroup which is isomorphic to C2 squared, the Klein-Ford group in C3 semi-direct D4. And for that group C2 squared, we show Y at X is not C2 squared equivalent birational to each other. So lastly, here's another small implication of our work. So this is a theorem by Bouvel. He showed that here the field is any field of characteristic 0. He showed that, well, for smooth cubic threefold, the following are equivalent. The first, Y is Pfaffian over K, and second, exists a normal quintic genus 1 curve in X over K. So the theorem by Bouvel is much more general. It's for arbitrary degree D hypersurface. I think in P4 and P5. He shows being Pfaffian is equivalent to the existence of some codimension 2 subscheme in X, in Y with certain properties. But here I stated for the cubic threefold. And this is also how he proves every smooth cubic threefold over algebraically closed field is in fact Pfaffian. Because each of them contains the normal quintic genus 1 curve. Well, this result has also been generalized to singular cubic threefold. So we now know that every singular cubic threefolds over an algebraically closed field is Pfaffian. So one reason people care about, well, we care about equivariant geometry is that it's sort of an analog of the algebraic varieties over non-closed field, where you can think of the automorphism group action as an analog of the Galois action over non-closed field. So here's is a statement over any field of characteristic 0. You can ask what happens equivariantly. So namely, is this equivariant analog holds? So it's the following equivalent. First is your group action on Y is equivariantly Pfaffian, and the second is Y contains a G invariant normal quintic genus 1 curve. It turns out the answer is no, because the second one, if Y contains a G invariant normal quintic genus 1 curve, by Finally-Skovsky, we know this gives a birational map to X, which is the degree 14 Fano threefold. And if the curve is G invariant, the birational map will be G equivariant. However, our results shows that we provided examples where the birationality between X and Y actually fails G equivariantly, and in particular for the group PSL 211 and C3 semi-direct D4. So the answer of this equivariant analog is no. It could be also an interesting problem to explore, and criteria for the existence of equivariant Pfaffian actions in general for any degree D hypersurface, for example, because here in our work, the proof is not conceptual. It's just just an enumeration of the possible groups which can act and check the representation. So it would be nice to have more geometric criterions for being equivariant Pfaffian. And that will be all of my talk. Thank you very much.